Welcome to the next section of refrigeration system. Now before we go into the detail, let's have a brief outlook about the previous lecture. In the previous lecture we discussed about the refrigeration system and its component, and we had a discussion about the various kind of auxiliary devices, accumulators, receivers, oil splitters, stainers, dryers, and we had a discussion about the check valves and solenoid valves. Apart from this, we performed the vapor compression refrigeration cycle under the edges of energy analysis, exergy analysis. Now, in this particular lecture, we are going to discuss about the refrigeration system, in which we will discuss about the cascade refrigeration system, where we will discuss about the two-stage cascade refrigeration system or three-stage cascade refrigeration system. Apart from this, we will discuss about the absorption refrigeration system or ARS, in which we will discuss about the ammonia-water ARS, gas diffusion ARS, water lithium bromide absorption refrigeration system. Under this, we will discuss about the single stage absorption refrigeration system and double stage absorption refrigeration system. Then we will discuss about the practical vapor compression refrigeration cycle, and lastly we will discuss about the multi-stage refrigeration system. Now let us talk about first about the refrigeration cycle. There is the practical vapor refrigeration cycle. Now there are some differences between the practical and theoretical cycle, primarily due to the pressure and temperature drop associated with the refrigerant flow and heat transfer to or from the surrounding. Now in compression process, due to irreversibility, you cannot avoid the irreversibility. So due to irreversibility and heat transfer either due to or from surrounding, depending upon the temperature of refrigerant and surrounding, entropy may increase for irreversibility and heat transfer to the refrigerant. Now it may decrease for irreversibilities, heat transfer from the refrigerant. Now here you see that in this particular figure, we have shown this in the dotted line from 1 to 2 and 2 dash. Now here this is the simple refrigeration system or vapor compression refrigeration system. Here you are extracting QL amount of heat from a body which is maintained at low temperature. So sometimes it is referred as a source, and here this is the sink. So from here evaporator you are extracting QL amount of heat, and it's subjected to the compressor. Then this is a condenser through which you are discharging this QH amount of heat to the sink or a hot surface body, and again it restored to the saturated liquid shape. Through the expansion valve, it again go back to the evaporator. So this entire system thermodynamically is depicted in this TS diagram. Now the pressure of the liquid leaving the condenser become lesser than the pressure of vapor entering, and the temperature of the refrigerant in the condenser, it is usually higher than that of the surrounding. So as always, the temperature of the liquid leaving the condenser is lower than the saturation temperature. Now there is more drop in the piping between the condenser and expansion valve. So from 3 to this stage, there are temperature drop. Now this is gain because of this heat transfer. The refrigerant enters the evaporator with a lower enthalpy, which permit more heat to be transferred to the refrigerant in the evaporator. So that's why this is a gain, and efficiency of your refrigeration cycle can be improvised. Now there is also some pressure drop in the refrigerant flow through the evaporator. It is quite obvious. Now it may be slightly superheated as it leaves the evaporator, and through heat transfer from the surrounding, its temperature increase in the piping between the evaporator and the compressor. Now this heat transfer represents a loss because it increases the work of the compressor, since the fluid entering it has an increased specific volume. Now here you see this is a typical commercial refrigeration unit. This shows all its component. Now here you see that this is the evaporator or evaporating fan, and you need to have a temperature control. So thermostat control is there. Then here you see that this is the expansion valve, and here you see that this is the main compressor unit with the accumulation. So all kind of auxiliary setup they are there, and this is your condenser. And again you are having this condensing fan with the high pressure side. So this is the typical commercial refrigeration unit. Now let's talk about the purging air in the refrigeration system. Now air is the enemy of any kind of refrigeration system. Therefore, you have to remove the air in case if it is entrapped. So by removing air, we can maximize the refrigeration system performance, and sometimes referred with respect to the coefficient of performance. The failure to remove air can be costly in terms of the operating efficiency, or sometimes it may lead to the equipment damage. Now such damage are especially notable in the industrial sized refrigeration system such as cold storage facilities, food processing plants, and sometimes the chemical plants. Now the process of removing air which is colorless and odorless is called purging. Now it become more important to understand that why, where and how the purging of the system takes place. Now this is a typical photograph of air purger. Now air can enter a refrigeration system by several ways or several places. Like when suction pressure is below atmospheric condition, air can enter through seals and valve packing. Air can rush in when the system is open for repair, coil cleaning or any kind of addition of equipment. Air can enter when the refrigerant truck is charging the system or when oil is being added. So the purging of the refrigeration system can be done by automatically or manually. Now there are various methods for air purging. And broadly you can say there are two methods of purging of a system. One is the manual, or second one is the automatic. Now to purge manually, a properly positioned valve is opened by hand, allowing the air to escape. Now it is a misconception that when a cloud of refrigerant gas is seen being discharged to atmosphere, the system has been purged of gas. Therefore many times automatic purging is required or referred or recommended. Automatic purgers. The automatic purging, there are two types of automatic purgers such as non-electrical mechanical, and second one is the automatic electronic purger. The non-electrical mechanical units, they are used primarily in the application where electricity is not available at the point of use or in hazardous application. They remove air by sensing the density difference between the liquid refrigerant and gases. Now an operator opens and closes valve to start and stop the purging operation and ensure its efficiency. The electronic automatic refrigeration purgers are classed as a single point and a multi-point purgers. The single point electronic refrigerated purger has mechanical purge operation with a temperature or gas level monitor that controls the discharge to atmosphere. A multi-point refrigerated purger will purge a number of points using the same unit. However, each purge unit is purged individually, and multi-point purger offer total automation including startup, shutdown and alarm features. Now here you see that the refrigeration with the multi-point automatic purger. Now this is the electronic purger control, and you see all the major operations are enlisted, and this is the purging valve. So you can see that the attachment of purging device in this particular refrigeration apparatus. Now let's talk about the multi-stage refrigeration system. The multi-stage refrigeration system, they are widely used where ultra low temperature are required, but cannot be obtained economically through the use of a single stage system. Now due to compression ratio, they are too large to attain the temperature required to evaporate and condense the vapor. Now there are two general type of such system. One is the cascade and second one is the multi-stage. So in multi-stage system, there are two or more compressor, they are connected in series in the same refrigeration system. The refrigerant become more dense vapor while it passes through each compressor. a two-stage system can attain a temperature of approximately 65 degrees Celsius and three-stage about minus 100 degrees Celsius. Where large temperature and pressure differences exist between the evaporator and the condenser, the multi-stage vapor compression system are employed accordingly. Now, there are various disadvantages of high compression ratio. One is that the decrease in the compression efficiency. Second is the increase in the temperature of the refrigerant vapor from the compressor. And third one is the increase in the energy consumption per unit of refrigeration production. Now, here you see that this is the two-stage vapor compression refrigeration system. Now, here this is the evaporator through which you are extracting the QL amount of energy from a low temperature source, and this is the two compression unit. One is the low pressure compression unit and second one is the high pressure compression unit. So, and this is the mixing chamber, it is quite obvious, and this is subjected to the condenser where you are discharging the QH amount of the heat to the sink. Apart from this, the expansion valve, this is attached with the flash chamber. Now, if you wish to represent this particular entire operation into the TS diagram, here you see that all the steps are demarcated. Now, let us talk about the cascade refrigeration system. Now, for industrial application which requires sometimes moderately low temperature and refrigeration, they operate in two or more stages, that is sometimes called that two or more cycle in series. The cascade system, they are employed to obtain high temperature differential between the heat source and heat sink and are applied for temperature ranging from minus 70 degrees Celsius to 100 degrees Celsius. The cascade refrigeration system, they are commonly used in liquefaction of natural gas and some other gases. The refrigerants can be chosen with the appropriate properties, avoiding large dimensions for the system component. Now, in these type of system, multiple evaporators can be utilized in any one stage of the compression. The refrigerant used in each stage may be different and are selected for optimum performance at given evaporator and condenser temperatures. Two-stage cascade system can be used in two different refrigeration systems. They are connected in series to achieve the temperature of around say minus 85 degrees Celsius. Now, let us talk about the two-stage cascade system. The two-stage cascade system employs two vapor compression units working separately with the different refrigerants and interconnected in such a way that the evaporator of one system is used to serve as the condenser to a lower temperature system, and that is evaporator from the first unit cools the condenser of the second unit. Now, the cascade arrangement, this allows one of the unit to be operated at a lower temperature and pressure. It also allows two different refrigerant to be used and it can produce temperature below minus 150 degrees Celsius. Now, because single system cannot achieve high compression ratio necessarily, now here you see that the practical two-stage cascade refrigeration system. Now here this is the low stage compression and this is the high stage compression. So by this way you see that we are using two-stage cascading refrigeration system. Apart from this, heat exchanger and the condenser and evaporator. So what we discussed in the previous slides, it is quite obvious in this particular figure. Now, here we showed that two-stage cascading refrigeration system. The condenser of system 1, now this is the system 1, the condenser of the system 1 called the first or high pressure stage is usually fan cooled by the ambient air. The evaporator of system 1 is used to cool the condenser of system 2 and that is called the second or low pressure stage. The unit that makes up the evaporator of system 1 here and the condenser of the system 2 is often referred to as an interstage or cascading condenser system. Now, here you see the TES diagram of the two-stage cascade refrigeration system and the pH diagram, log pH diagram of two-stage cascade system. Now let's talk about the three-stage cascade refrigeration system. The cascade refrigeration cycles, they are commonly used in the liquefaction of natural gas, which consists of hydrocarbon of the paraffin series, of which methane has the lowest boiling point at atmospheric pressure. The refrigeration down to the temperature can be provided by the ternary cascade refrigeration cycle using propane, ethane and methane, whose boiling point at standard atmospheric pressure are 231.1 Kelvin, 184.5 Kelvin and 111.7 Kelvin respectively. The compressed methane vapor first cooled by the heat exchanger with ethane in the ethane evaporator, hence reducing the degree of irreversibility involving in cooling and condensing methane. Also, because of high temperature after compression, the gas leaving such compressor passes first through a water cooled after cooler. In large scale plant of such type, the compressor become rotary turbo machine instead of reciprocating type. Now here you see this is the typical figure of three-stage cascade vapor compression refrigeration system. This is the propane, ethane and a methane. Now let's talk about the energy and exergy analysis of cascade refrigeration system. Now in this analysis, the methodology of writing the mass, energy and exergy balance equation is the same as for the vapor compression refrigeration system, except the work input to the compressor will be total work input, which is the summation of all compressor work. The coefficient of performance or COP, this becomes different. That is the overall COP for three-stage cascade refrigeration system. This can be defined as 1 plus 1 upon COP T is equal to 1 plus 1 upon COP1 into 1 plus 1 upon COP2. Now COP total, that is less than either of COP1 and COP2, because the COP of a refrigeration cycle decrease with increase in reservoir temperature. Let's talk about the liquefaction of gases. Now it is important area of refrigeration, as many of the engineering processes are cryogenic temperature below 100 degrees Celsius, minus 100 degrees Celsius, depends upon the liquefied gases. Some example includes the separation of oxygen and nitrogen from air, preparation of liquid propellant for rockets. The substance exists in the form of gas phase only at temperature above the critical point. The critical temperature of some of the gases such as helium, hydrogen and nitrogen are 268, minus 240, minus 147 degree Celsius respectively. Now let's talk about the absorption refrigeration system or ARSs. Now absorption refrigeration systems are similar to the vapor compression refrigeration cycle, except the compressor of the vapor compression cycle is replaced by three elements such as absorber, a solution sump and a generator. Now there are three steps including absorption, solution sumping and vapor release take place in ARS. Now here you see a basic ARS, which consists of an evaporator, a generator, a condenser and an absorber. Apart from this, a solution pump and two throttling valves. Now here you see that we are having two throttling valves and this is the solution pump. Now in this particular process, a mixture of a strong refrigerant and absorbent is heated in a high pressure portion of the system, and that is called a generator. The hot refrigerant vapor is cooled then in the condenser until it condenses completely. The refrigerant liquid is then passed through the throttling valve into the low pressure portion of the system, and that is evaporator. Now this reduction in the pressure through the valve facilitates the vaporization of refrigerant, which affects the heat removal from the medium. The weak refrigerant flows down through a throttling device to the absorber. Now, after the evaporator, the cold refrigerant comes to the absorber and absorbed by the weak solution, that is absorbent, and due to strong chemical affinity of each other. The strong solution is then obtained and the pump by a solution pump to the generator, where it is again heated and the cycle continues. Now, the system operates at high vacuum at an evaporator pressure of 1.0 kilopascal and generator and condenser operates at 10 kilopascal, and that is significant. The advantage of ARS over the refrigeration system, there are different type of advantages attributed to the ARS over the refrigeration system, such as they are having a quiet operation, noiseless, they are having the long service life, no cycling losses due to on-off operation, they meet the variable load easily and efficiently, they possess the high degree of reliability, and they are efficient and economic with respect to the use of low grade energy source such as solar energy, waste energy and geothermal energy. Now, when we talk about the application of various ARS in different industries, one is petrochemical or chemical industries for liquefying of gases and separation processes, cold storage, refrigeration system, cogeneration units in combination with the production of heat and cold, food industries like meat, dairy, vegetable and food freezing and storage, fisheries and freeze drying. Now, here you see that application of ARS in 2500 kilowatt at minus 15 degrees Celsius in meat factory, and this ARS is installed in a refinery of 2700 kilowatt. Now, let us talk about the ammonia-water ARS. Now, this is the practical absorption refrigeration system using ammonia as an refrigerant and water as an absorbent, and they are as a working fluid with the two heat exchangers. Now, in this process, with the use of two heat exchangers, an analyzer and rectifier are also used, and this device is used to remove the water vapor formed in the generator so that only ammonia vapor goes to the condenser. Now, in this particular figure, this shows a practical approach to ammonia ARS. Water is utilized to absorb and release the ammonia as a refrigerant. The amount of ammonia vapor can be absorbed and held in water solution increases with the increase in the pressure and decreases with the increase in the temperature. The operation of such type of system are same as that of basic ARS, but additional analyzer, rectifier and heat exchanger are used in ammonia ARS. Sometimes the complete equilibrium saturation may not be reached in the absorber, so the strong solution leaving the absorber may not be as fully saturated with water at its temperature and pressure. The strong solution obtained from the absorber enters into the solution pump, where raise in the pressure and delivers the solution into the generator through the heat exchanger. The strong solution pumped into the generator via heat exchanger, where a strong solution is preheated before being discharged into the ammonia generator. The generator, which is heated by an energy source, raises the temperature of a strong solution and causing the ammonia to separate from it. The remaining weak solution, it absorbs some of the water vapor coming from the analyzer, rectifier, which is in combination, and flows down to the expansion valve through the heat exchanger. It is then throttled into the absorber for further cooling as it picks up a new charge of ammonia vapor, thus becoming a strong solution. The hot ammonia in the vapor phase from the generator is driven out of solution and rises through the rectifier for possible separation of the remaining water vapor. Now, then it enters into the condenser and released to the liquid phase. The liquid ammonia enters the second heat exchanger and loses some heat to cool ammonia vapor. The cycle is completed when the desired cooling load is achieved in the evaporator. Cool ammonia vapor obtained from the evaporator passes into the absorber and is absorbed there. Now, when the vapor goes into the liquid solution, it releases both its latent heat and heat of dilution. The heat introduced into the absorption system in the generator from steam heat and the evaporator, that is from the actual refrigeration operation, has to be rejected to outside, that is to the sink. Now, two heat rejection take place in the system, first in ammonia condenser and other is in ammonia absorber. Water can absorb ammonia and stay in the solution under normal temperature. Therefore, absorber has to be cooled with cooling water. The evaporated ammonia in the generator is passing through the distillation column, where ammonia is concentrated into the pure ammonia vapor before going to the condenser. When ammonia is turned into the liquid, it goes to the evaporator low pressure side, where ammonia is again turned into vapor. The ammonia vapor is then absorbed in the absorber to complete the cycle. Now, let us talk about the gas diffusion or 3-fluid ARS. In such type of system, there are 3 fluids used as a working media. The most commonly used fluid in question, they are ammonia as refrigerant, water as absorbent and hydrogen as carrier gas. The system consists of 4 main parts such as boiler, condenser, evaporator and absorber. The burner and electric heating is also used to supply the heat in the gas unit. Such type of systems are used in the domestic application where coefficient of performance is not important, then quite trouble-free operation. Now, here you see the cold ammonia vapor with hydrogen is circulated by natural convection through the gas-gas heat exchanger to the absorber, where ammonia is in contact with the weak solution from the separator. Now, the absorption of ammonia and hydrogen takes place at low temperature, and so hydrogen alone passes through the heat exchanger to the evaporator. The strong solution flows down by the gravity. Let us talk about the water lithium bromide. Now, in such type of ARS, water, that is as a refrigerant, and lithium bromide as absorbent, they are used as a working fluid. Now, these systems are also known as absorption chillers and have wide application in air conditioning and chilling or pre-cooling operation. Now, there is lowest evaporation temperature of say 4 degrees Celsius due to use of the water as refrigerant. Lower pressure steams are used as a heating media. The coefficient of performance are less than unity, but due to cheap energy source used, the system is economical. The evaporator and absorber are combined in shell at lower pressure level, and condenser and generator are combined in another shell at high pressure level. Liquid-liquid heat exchanger is arranged and used to increase the system efficiency and coefficient of performance or COP. The crystallization is the main problem in this particular case due to the solidification of lithium bromide. The absorption chillers are classified into 2 categories. One is the single stage and next one is the double stage ARS. Let us talk about the single stage or single effect ARS. Now, this particular figure shows the single effect evaporator with an absorber. There is a generator and a pump and a heat exchanger. The high pressure liquid refrigerant from condenser, this passes through the metering device. The resulting vapor nitrates to the lower pressure absorber, there it is absorbed by lithium bromide solution. Now, this process is low pressure area and draws a continuous flow of refrigerant vapor from evaporator to the absorber and also causes the vapor to condense as it releases the heat of vaporization in the evaporator. The solution of in the refrigeration cycle must be reconnected as accomplished by constantly pumping and a dilute solution from the absorber to the generator. Now, here the addition of heat boils the refrigerant from the absorber. Once the refrigerant is removed, the reconcentrated lithium bromide solution return to absorber and ready to resume the absorption process. The refrigerant vapor migrates to the condenser and there the refrigerant return to the liquid state as the cooling water pick up the heat of vaporization carried by vapor. Then the liquid refrigerant returned to the metering device to complete the cycle. Now, let's talk about the double effect ARS. This particular figure shows the double effect ARS with an absorber, 2 generator pump and 2 heat exchanger and 2 condensers. Now, here the double effect ARS, the energy efficiency of absorption can be improved by recovering some of the heat rejected to the cooling tower circuit. The vapor driven off by the heating in first stage concentrator to drive off more water in second stage. In this system, 2 single effect cycles are stacked on top of each other with 2 separate shells. A smaller one is the first concentrator or generator. The temperature, pressure and solution concentration within the larger shell are similar to single effect ARS. The cycle on the top is driven either directly by natural gas or oil burner or indirectly by using steam. The heat is added to the generator on the top of the cycle, which generates the refrigerant vapor at higher temperature and pressure. The vapor is condensed at higher temperature and pressure, and the heat of condensation is used to drive the generator of bottom cycle, which is the lower temperature. Now, if heat added to the generator is equivalent to the heat of condensation of the refrigerant, then there is an improvement in the efficiency. So, in this particular lecture, we discussed the different type of ARS, keeping in view of vapor compression refrigeration cycle. And for your convenience, we have enlisted couple of references. You can go through all these references if you need the further knowledge or information. Thank you very much.